All right, hello viewers here. Welcome to my YouTube channel, Mathematics Made Easy. So in today's video, we have this beautiful integral. So we have integral from 0 to infinity of arcsinh of cosec of x dx. So that is the integral I want to solve in today's video. Okay. So if you are new to this channel, please don't forget to subscribe to my channel, like my videos, comment, and also share. All right, guys. Now let's dive into the solution. Now, how are we going to solve this problem? The first thing we're going to do now is to recall, this identity. Okay, so recall that, arcsine of x, okay, is equal to log x plus, square root of 1 plus x to the second power. Are we together now? So this is arcsine of x in terms of logarithm, all right, in form of logarithm. And also recall that cosec of x, okay, this is equal to 2 over exponential x minus exponential negative x, all right. This is cosec x in terms of, exponential form. Now, what are we going to do? So what we are going to do now is to simplify arcsine of cosec of x. So for us to be able to solve this problem successfully with ease. All right, now let's do that. Simplifying this, we have arcsine of cosec of x. So this would now be equal to, so instead of us writing arcsine of x, we have log. Then instead of you writing x, we have 2 over exponential x minus exponential negative x. So this will be 2 over exponential x minus exponential negative x, then plus, square root of 1 plus x squared. That's square root of 1 plus, x is 2 over exponential x minus exponential negative x, then everything to the second power. Now this is beautiful and cool. So now let's move on. This will now be equal to log 2 over exponential x minus exponential negative x, then plus, square roots of 1 plus. Now 2 to the second power will give us 4. So we have 4 over, we have exponential x minus exponential negative x also to the second power. Then we close the bracket. Now moving on, we have to simplify this term inside the square root. So if we simplify the term inside the square root, what we're going to have? So we have the following. We have log 2 over exponential x minus exponential negative x plus square roots of 1. The LCM is exponential x minus exponential negative x. So let's write out the LCM rather, exponential x minus exponential negative x to the second power. And don't forget it's over 1. How many one can we see this? That is what? Exponential x minus exponential negative x to the second power, then plus 4. So we close the brackets. So this is equal to log 2 over exponential x minus exponential negative x plus square roots of, now if you expand exponential x minus exponential negative x, so this will give you exponential 2x plus exponential negative 2x, then minus 2 plus 4. Then everything here over exponential x minus exponential negative x to the second power. Then you close the bracket. Now negative 2 plus 4 will give us 2. Okay, so we have log 2 over exponential x minus exponential negative x plus square root of exponential 2x plus exponential negative 2x plus 2. Negative 2 plus 4 is now 2. Then everything over exponential x minus exponential negative x to the second power. All right, now if you if you factorize exponential 2x plus exponential negative 2x plus 2, if you factorize that, that will give you exponential x plus exponential negative x to the second power. All right, so this will now be equal to log 2 over exponential x minus exponential negative x, so plus square root of, so don't forget, if you factorize this, we have exponential x minus plus exponential negative x to the second power, then everything over exponential x minus exponential negative x to the second power. Now this is cool. if you take the square root of this, the square is going to cancel out the square root. Then we have log 2 over exponential x minus exponential negative x, then plus exponential negative x, then everything over exponential x minus exponential negative x. Then you close the bracket. So we have our LCM, which is exponential x minus exponential negative x. So this is equal to log, okay, 2 over exponential x minus exponential negative x, then plus e raised to the power of x plus e raised to the power of negative x. All right, so that's what we're going to have now. Now, moving on, guys, we have simplified this. Then it's remaining one last step for us to be able to simplify this completely. Now, what is the last step I'm talking about? So this is what I'm going to do. I'm going to multiply both the numerator and the denominator by exponential x. All right. So if I do that, I'm going to have this. So I have log exponential x, then into bracket 2 plus exponential x plus exponential negative x. Okay. Then over exponential x, then into bracket exponential x minus exponential negative x. So this is equal to log, if you open the bracket with exponential x in the numerator, we have 2 exponential x plus exponential 2x, then plus 1. Because exponential x multiplied by exponential negative x, according to law of indices there, that will give you exponential x minus x, which is exponential 0. And any number raised to the power of 0 will always give us 1, except 0 raised to the power of 0. Okay? So that's why we have 1 here. Then everything over, so exponential x multiplied by exponential x here also, that will give us exponential 2x. And then exponential x multiplied by exponential negative x, that will give us plus 1. I mean 1. And then don't forget the sign. We have minus 1. Yeah, that's actually cool. Now, if you factorize 2 exponential x plus exponential 2x plus 1, so that will surely give us exponential x plus 1 to the second power. All right. So finally, we have log exponential x plus 1 to the second power, then over. Now, we also factorize this denominator exponential 2x minus 1, difference of 2 square, a square minus b square. This will give you a minus b multiplied by a plus b, difference of 2 square. So this will also give us exponential x plus 1, all right, then multiply by exponential x minus 1. Yeah, this is cool. So what are we going to have now? We have, exponential x plus 1. We cancel 1 out of this guy. So we have log, exponential x plus 1 over exponential x minus 1. You can see this is actually beautiful and cool. So we've simplified arcsinh of quotient of x to be what? Log exponential x plus 1 over exponential x minus 1. We have to assume that we are working with a natural log. In this case, this is integral, so we are working with natural log. Are we together now? Now, what we're going to do now is to evaluate or to now integrate log exponential x plus 1 over exponential x minus 1, from 0 to infinity. Let's do that now. All right, so we have integral from 0 to infinity. Action of cosec x dx is now equal to integral from 0 to infinity log exponential x plus 1 over exponential x minus 1 dx. So that is what we have now. So how we're going to solve this beautiful integral? Now, this is what we're going to do. We're going to mix of substitution for us to be able to solve this integral. Okay, with ease, we're going to make use of substitution. So what substitution are we making here? Now, you can see that this integral is 0 to infinity. So I want to transform this integral to be what? From it has 0 to 1. Understand? So how can I do that? Remember 1 over infinity is 0. So how can I have 1 over infinity? So I have to make use of substitution that will make me to have 1 over infinity so that infinity will turn to 0. All right. Now, let's do that, guys. So this is what we're gonna do. Remember, or let's just make a substitution. We are not remembering anything here. So let's say let lambda be equal to exponential negative x. So if lambda is exponential negative x, what is exponential x? The exponential x will be what? 1 over lambda. All right, that is the inverse of the lambda. Do you get what I'm saying now? If lambda is exponential negative x, so exponential x will be what? 1 over lambda. Right? Then you differentiate. So we differentiate lambda, we have the lambda, Then if we differentiate the exponential negative x, we have negative exponential negative x dx. Then if you make dx the subject of the formula, so we have dx, okay, is equal to negative 1 over exponential negative x, the lambda. I remember that exponential negative x is lambda, so this will be equal to negative 1 over lambda, the lambda. This is actually cool. Now let's talk about the limits. When you substitute x to be infinity, so exponential negative infinity, that will give us 0. And when you substitute x to be 0, and exponential 0 is what? 1. So we can now write the integral as follows. So if you write the integral, we have integral, from 0 now to, from 1 to what? To 0. Because if you substitute x to be 0, we have 1. And if you substitute x to be infinity, we have 0. So we have log. So instead of you writing exponential x, remember I said exponential x will be what? 1 over lambda, since lambda is exponential negative x. So definitely exponential x will be 1 over lambda. Okay, so plus 1 over, so exponential x, which is now 1 over lambda, okay, then minus 1. The x is now negative 1 over lambda, the lambda. All right, so let's do that. Negative 1 over lambda, okay, the lambda. Now this is what you're gonna do. This is your logarithm. You can multiply both the numerator and the denominator by lambda. And before that, we can switch these limits because of this negative sign. So if we switch the limit, this negative sign, we move out. So we're going to have integral from 0 to 1 now. So now let's do that. So this will be equal to integral from 0 to 1, then of log. So if you do what I ask you to do now, that is, you multiplying both the numerator and denominator by lambda. So lambda multiplied by 1 over lambda will give us 1. Okay, plus lambda multiplied by 1 is lambda. Then over lambda multiplied by 1 over lambda here is what? 1. And then lambda multiplied by negative 1 will give us negative lambda. All right, so we have multiplied by 1 over lambda. Okay, the lambda. Yeah, this is very cool, beautiful. All right, very cool and beautiful. So what are we going to do next? What are we going to do next? What are we going to do next? Now, this is what we are going to do next. So remember that if you have log a over b, so this is equal to log a minus log b. Remember that, all right? Remember that. That's log a minus log b. So we're going to apply that rule in this particular integral. So if you apply the rule here, so we're going to have integral from 0 to 1, okay, then of log 1 plus lambda, then minus log 1 minus lambda, then multiply by, this 1 over lambda outside. So everything multiplied by 1 over lambda. Let me just put it here, 1 over lambda. So multiply by everything here. Then the lambda. So you can open the bracket. So we open the bracket. So this integral will be splitted into two integrals. So we have integral from 0 to 1 of 1 over lambda, then of log 1 plus lambda, right? Then minus, don't forget the lambda, okay? Then minus integral from 0 to 1 of 1 over lambda, then of log 1 minus lambda, and don't forget the lambda. Yeah, this is cool and beautiful. Now we have that, guys. Now, what we're gonna do now is to integrate the two integrals separately. So we call this integral A, we call this integral B. Now let's solve this integral A. So now solving the integral A, so we have A is equal to integral from 0 to 1 of 1 over lambda of log 1 plus lambda, the lambda. Now I'm going to solve this integral. Now this one I'm going to use, I'm going to use the series representation of log 1 plus lambda. Okay, so remember that log 1 plus lambda, so this is equal to negative sum of k from 1 to infinity of minus 1 raised to the power of k of lambda raised to the power of k, then over k. That is log 1 plus lambda. All right, so we can now write this our integral as follows. So we have a is equal to integral from 0 to 1 of 1 over lambda. So instead of you writing log 1 plus lambda, so I'm going to write negative sum of k from 1 to infinity of minus 1 raised to the power of k, lambda raised to the power of k, then over k. Okay, then we have the lambda. Yeah, this is actually cool. Now, according to the Frobenius rule, so we can bring out the what? The sum. So we bring out the summation sign with a negative sign there. So we have a is equal to negative sum of k from 1 to infinity of minus 1 raised to the power of k over k, then integral from 0 to 1 of 1 over lambda multiplied by lambda raised to the power of k, the lambda. Then if you apply the law of indices here, 1 over lambda multiplied by lambda raised to the power of k. So that will be lambda raised to the power of k minus 1, okay? Law of indices. So, which is now equal to minus sum of k from 1 to infinity of minus 1 raised to the power of k, then over k, so of integral from 0 to 1 of lambda raised to the power of k minus 1, the lambda. Now, if you solve this integral, your elementary integral, so lambda raised to the power of k minus 1 plus 1 over k minus 1 plus 1, if you have integral of lambda raised to the power of k minus 1, the lambda, so this will give you lambda raised to the power of k minus 1 plus 1, okay, over k minus 1 plus 1. Then you add your plus c, so which is now lambda raised to the power of k over k, then plus c. But here we are now adding plus c because we have the limit. The limit is from 0 to 1. Just apply your limit. So when it is 1, you have 1 over k, and when it is 0, that will be 0, okay? So we have a is now equal to negative sum of k from 0 to infinity of minus 1 raised to the power of k over k, then of, so instead of us writing integral from 0 to 1 of lambda raised to the power of k minus 1, so we're going to write lambda raised to the power of k over k, then you apply the limit from 0 to 1. So therefore, this is equal to negative sum of k from 1 to infinity of minus 1 raised to the power of k over k. So if you apply your limits, when lambda is 1, you have 1 over k, and when lambda is 0, you have 0. So we have multiplied by 1 over k. That shows that k multiplied by k will give us k to the second power. K to the second power. So we have a is equal to negative sum of k from 1 to infinity, okay, of minus 1 raised to the power of k over now k multiplied by k will give us k to the second power. All right, so remember that this is equal to, if you have this kind of sum, if you have sum of k from 1 to infinity of minus 1 raised to the power of k over k raised to the power of s, so this is equal to eta of s. All right, so in this case your s is 2, so definitely we have a is equal to negative eta of 2. And remember, eta of 2 is negative pi square over 12. This will be minus into bracket negative pi square over 12. And negative times negative will give us positive. So we have positive pi square over 12. All right. So that is the answer to the integral A. We have two integrals we want to solve. So integral A is solved already. So let's move to integral B. So we have our integral B. So integral B is integral from 0 to 1 of 1 over lambda log 1 minus lambda a lambda. So that's integral B. Now, how are we going to solve integral B? Now we are going to use same method that we use for integral A by making use of the the series representation of log 1 plus lambda in integral A. Now, what is the series representation of log 1 minus lambda? Now, we know that log 1 minus lambda, write it here, log 1 minus lambda, so this is equal to, negative, sum of k from 1 to infinity of 1 over, lambda raised to the power of k over k. So this is log 1 minus lambda. So we can now write this, our integral, as follows. So you have b is equal to integral from 0 to 1, okay? So of 1 over lambda. So instead of you writing, log 1 minus lambda, so we can now write negative sum of k from 1 to infinity of lambda raised to the power of k over k the lambda. So we cannot bring out the sum. So we bring out the sum. So this will be equal to negative sum of k from 1 to infinity, okay, then of integral from 0 to 1, so of 1 over lambda, then multiply by lambda raised to the power of k, the lambda. Then if you make use of the law of indices right here, lambda raised to the power of k over lambda, so that will be lambda raised to the power of k minus 1. So we have b is equal to negative sum of k from 1 to infinity of integral from 0 to 1 of lambda raised to the power of k minus 1, the lambda. And then we already solved this earlier in integral A, which is lambda raised to the power of k over k. So this is now equal to negative sum k from 1 to infinity. Sorry, don't forget this. 1 over k. We forgot to put it out. Very sorry for that. 1 over k. Okay, so we have 1 over k then of lambda raised to the power of k over k, then you apply the limit 0 to 1. So therefore we have b is equal to negative sum of k from 1 to infinity of 1 over k. So if you apply your lambda to be 1, we have 1 over k. If you apply your lambda to be 0, we have 0. So k multiplied by k will give us k to the second power. So we have negative sum of k from 1 to infinity of 1 over k to the second power. All right, now don't forget, this is in form of this sum. If you have sum of k from 1 to infinity of 1 over k to the power of s, so this is equal to zeta of s. Now in this case, your s is 2. So this is equal to negative zeta of 2. And remember, zeta of 2 is pi raised to the power of 2 over 6. So definitely we have b to be equal to negative pi square over 6. That's the value of b. All right, now let's solve this problem finally. We know that our integral I is equal to a minus b, and then we have a to be pi square over 12, and b is now negative pi square over 6. Now minus times minus will give us plus. So we have pi square over 12 plus pi square over 6. So the LCM of 12 and 6, that is 12. So we have 12, 12 and 12, that is 1, 1 times pi square. So we have pi squared. And then 6 in 12, that's 2, 2 times pi square. So we have 2 pi squared. Then pi square plus 2 pi square will give us 3 pi square over 12. So which is equal to pi square over 4. So that is the final answer to that problem. Alright, so if you like this kind of video, please don't forget to subscribe to my channel, like my videos, comment, and also share. Thanks for watching, guys. See you next time. Goodbye.